right. Good afternoon. Welcome back to Codex. So many, but not all, of our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we're very happy to have Mikhail Gansenov to be our next speaker in this series. Mikhail is currently a graduate student at Aalto University in Finland, with a couple of years left in his studies. His research, advised by Professor Patrick Ostergaard, focuses on few equiangular line systems. We're excited to have him here to tell us about infinite families of optimal biangular line packings. Take it away.
Thank you, John, for the introduction. And thank you also for the opportunity to speak here. And hello, everyone. And since today we are going to speak about particular systems of few angular lines, I'm going to begin this talk by giving definition of few line systems and few language. We use a simple definition for line systems since we identify lines with corresponding unit vectors. And we define angles between lines as absolute values of inner products between the representative unit vectors. In other words, if an angle is 1, then corresponding lines are parallel, and if angle is 0, then lines are orthogonal. And in all other cases, we have something in between. An angle set of a line system is defined as collection of all angles between pairs of different lines in a line system. We want to restrict, exclude a situation where multiple vectors describe same lines, and thus we impose this condition which prevents that multiple vectors describe same line. We call a line system S angular is the cardinality of the angle set is at most S, and define a coherence of a line system as the largest angle in the angle set. And geometrically, this means that how small angular distance between lines in a line system can get. And from point of view of many applications, it's important to arrange lines in such a way that the minimal angular distance between lines is maximized. And this is same as minimizing coherence of the line system. This problem is called a line packing problem. Given number of lines in a given vector space. Solutions to line packing problem are called optimal line systems. And it often happens that optimal line systems lead us to some very fascinating math. Several nice line systems possess high degree of symmetry to the point that a line system can be obtained as an orbit of a single vector on the direction of some finite group of orthogonal transformations. On this slide, we have a simplistic example of that. We have a unit vector as well as group of 3 orthogonal transformations. First orthogonal transform is just identity, and the other two are rotations by 120 and 240 degrees. Once we apply this transformation to the initial vector, we get a nice line system consisting of 3 lines. Unfortunately, this simple example is not complicated enough to highlight the fact that choice of the initial vector is very important, since in this example, any initial unit vector will lead to essentially same line system, which will be just rotated version of this one. In order to give example of a more complicated situation, we need to move into 3-dimensional space, and we can take, for example, icosahedral symmetry group, which acts on a unit sphere by permuting these fundamental domains, which look like triangles in this image. And there are exactly 120 such fundamental domains, and there are 120 orthogonal transformations in this icosahedral symmetry group. A single fundamental domain can be permuted into another fundamental domain in exactly one way. By choosing some initial fundamental domain and taking for initial vector, for example, from this upper angle of the initial fundamental domain, and by applying our orthogonal transformations of this icosahedral symmetry group, we get a line system which consists from 6 lines, which are corresponding to vertices of regular icosahedron. However, we can take another initial unit vector from the unit sphere, for example, such vector which corresponds to rightmost corner of the same initial fundamental domain, and by spinning it by icosahedral symmetry group, we obtain a line system which will consist from 10 lines, and lines will be corresponding to vertices of regular dodecahedron. And as we see, these line systems are very different, despite they all having the same symmetries. And this is important, since later on we will need to choose our initial vectors in order to construct nice line systems. Okay, since we are interested in few angular line systems, more precisely into biangular line systems, we need to know what is the best case scenario for we can have for a line system with a prescribed angle set. And for angle sets which are small enough, this question might be answered by so-called relative bounds, which are originally obtained by Delsart, Waters, and Seder in the 70s. These are well-known results. Bianco, real Bianco version of this relative bounds is on this slide, and it tells us that number of biangular lines in n-dimensional real vector space with prescribed angles alpha and beta, which are small enough, is limited by this fraction. This relative bound is interesting for a couple of reasons. The first reason is the fact that we actually know several line systems which achieve equality in this bound. In other words, this bound is tight in some sense. The other reason is that such line systems seems to be very rare, and all of them are more or less remarkable. So this relative bound can be used as some sort of quality certificate for systems of biangular lines. In addition to this biangular relative bound for real lines, we have also similar bounds for systems of complex biangular lines, and also for line systems with any number of angular distances. And in fact, this can be obtained very easily. Line systems which achieve equality in the biangular relative bound are known to have special properties. I mentioned just a few of them. The first one is the fact that such line system is always projective to design. Converse is also true. And any biangular projective to design always achieves equality in the biangular relative bound. And for those of you who are not familiar with projective designs, those are finite collections of lines in finite dimensional vector space, such that average value of any even polynomial of degree twice the strength of design or less on the set of unit vector representatives equals average value of polynomial on the whole sphere. Basically, these are finite approximations to projective sphere. And second fact about systems which achieve equality in biangular relative bound is that if we fix one angle to be exactly 0, then the line system will be optimal by achieving equality in the second Levenshtein bound. And I wanted to mention this for a couple of reasons. The first reason is that achieving equality in the second or any Levenshtein bound is basically a nicest way to for a line system to achieve optimality. And the second reason is that this has among only few known ways to prove optimality of a line system. The other simple way to prove optimality of line system is to achieve equality in so-called orthoplex bound. In other cases, it often becomes very hard to prove optimality of a line system, and we know many positively optimal line systems which optimality cannot be proved currently. Okay, I mentioned that we can meet equality in the biangular relative bound, and here is complete list of line systems which are known to achieve equality in this bound. Those of systems on this list which have one of the angles 0, and also those which are equiangular lines achieve equality or achieve optimality by achieving equality in the second Levenshtein bound. And we see that we have a relatively small number of sporadic examples of such line systems, most of which come from two very remarkable lattices, namely Leech lattice and the E8 lattice. And in addition to these sporadic examples, we have two infinite families of line systems which are able to achieve equality in the relative bound. And it's interesting that in both cases, first members of these infinite families are also related to this E8 lattice. Namely, first member of the first infinite family can be constructed from root system of D4 lattice, while first member of the second infinite family can be constructed from the root system of E7 lattice. And both of these lattices are sublattices of the E8 lattice. The last infinite family, which I highlighted in green, is the new infinite family. And in this talk, we are going to construct line systems which belong to this infinite family. And as you see from the comment, these constructions can be obtained by studying representations of finite special linear loops. In complex vector spaces, we have a similar situation. I'm slightly less familiar with complex line systems, so maybe I missed some line systems on this table. But nevertheless, situation remains the same. We have a small number of sporadic examples. Most of them are related to complex reflection. In addition to this sporadic examples, we have also small number of infinite families. The first infinite family is only conjectured to be infinite, and it contains maximal sets of complex rectangular lines. The second infinite family is contains maximal sets of mutually unbiased bases, and the third infinite family is again a new infinite family, which it's possible to construct from representations of finite special element groups. And in similar way as in real counterpart, first member the third infinite family is more remarkable than other ones. Namely, it's actually tight projective tree design, which is related to Shepard-Todd complex reflection group with number 32. It's well known line system. Unfortunately, time will permit us. Time would prevent us from going into construction of these line systems, but the construction is very similar to the real infinite family, which we see here. And next, we are going to construct this real line systems of this green infinite family. And in order to do this, we need to introduce some notations. Most of these notations will be simple. First, we will need a finite field with Q elements, where Q is fixed to be power of 2. And next, we will need quadratic extension of field Fq. And elements of this extended field L can be expressed in the form which is described here. Namely, these are linear combinations of elements from field Fq and Fq multiples of a root of some irreducible quadratic polynomial. We will need several functions, namely absolute trace of the field Fq, which is simply sum of our Galois conjugates of element x. We will need relative trace of field L, which is again simply a sum of Galois conjugates of element z. And we will need relative norm of field L, which is a product of Galois conjugates of element z. And in addition to these expressions, we can also express this function in this form if we use this form of the element z. We will denote by Fq star a multiplicative group of the field Fq, and we define a unit circle of the field L to be a set of all elements of L with a norm 1. A unit circle is a multiplicative subgroup of the field L, and it contains exactly Q plus 1 elements. We continue with notations. We will need multiplicative characters of the unit circle, which can be defined through this formula, where this C0 is some generator of the unit circle. It's easy to see that there are in total 2 + 1 such multiplicative characters of the unit circle. We will also need an additive character of the field of Q, which is defined by this formula. By using our previous notations for a fixed multiplicative character of the unit circle P, we can define a so-called Bessel function of the field of Q by following characters, where additive character of the field L is summed against multiplicative character of the unit circle along the unit circle of the field L. And in some sources, these Bessel functions are known also as unitary Klosterman sums. And this is due to the fact because in ordinary Klosterman sums, unit circle is replaced by the hyperbola. And in order to see analogy between ordinary complex Bessel functions, we can compare these two formulas and see that finite sum is replaced by integral. And multiplicative character of the unit circle is replaced by the multiplicative character of the complex unit circle, and additive character of the field L is replaced by additive character of the complex numbers. It looks kind of funny in polar coordinates, but it's still an additive character. And in both cases, Bessel functions are parameterized by multiplicative characters of corresponding fields. And it's not a surprise that all kinds of Bessel functions and also ordinary Klosterman sums are related to representation theory of special linear group of second order. And in order to construct nice Lie systems, we are going to use following representations. These representations are well known and can be obtained through multiple ways. For example, Gelfand and Reif obtained these representations by decomposing Gelfand-Reif representations, while Tanaka obtained same representations from their representations. In both of these articles, results are obtained only for the case where characteristic of the finite field is odd. However, even characteristic case can be obtained similarly. If we look at these representations, we see that these representations are parameterized by multiplicative characters of the unit circle. We are not using a trivial character because it defines a two-dimensional representations, while our other multiplicative characters define Q-1 dimensional representations, which we will need. Every non-trivial character has a complex conjugate, and both character and complex conjugate are defined the same representation of this special linear group. Our representations are constructed in a similar way, where for every element of this special linear group, we attach a matrix TGP, which is Q-1 times Q-1 matrix, where entries are parameterized by elements of the multiplicative group of the field Fq. And entries of these matrices are computed according to this formula. Now, if G is upper triangular matrix, then the corresponding matrix TGP will be monomial. And in our other cases, matrices TGP will be related to Bessel functions, which we defined in the previous slide. So now we have a bunch of finite groups of orthogonal transformations. And in order to obtain some nice line systems, we need to choose somehow initial vectors, which we are going to spin by these orthogonal transformations. And such initial vector can be chosen to be any vector of the standard basis. And for every multiplicative character P, the resulting line system will contain Q2-1 lines, which will be seen from the fact that a line corresponding to this vector will be stabilized exactly by matrices TGP corresponding to elements G, which are upper ani-triangular matrices. In addition to that, if we spin initial vector by these monomial transformations, resulting orbit will contain all vectors from the standard basis. However, standard basis vectors are all contained as columns in the identity matrix, which is one among matrices TGP, namely corresponding to identity element of this special linear group. And from this, we can see that by multiplying any matrix TGP by the identity matrix, we obtain all orbit of the initial vectors as columns of matrices TGP. And since matrices TGP for a group for fixed P, it's easy to see that inner products between row and column vectors of these matrices is an entry in some other matrix TGP. But row vectors of matrices TGP are related to column vectors of some other matrix TGP, since which is inverse of the original matrix. And from that, we see that the angle set of a Lie system LP is determined by the absolute values of the entries of matrices TGP. More exactly, it consists from all absolute values of these entries, excluding absolute value 1, since in this case vectors will describe same lines. All line systems LP are projective 2 designs, and thus all the orbits of this initial vector are exceptional orbits, in the sense that the strength of resulting projective design is larger than usual. However, line systems LP are not necessarily biangular and not necessarily optimal. In order to achieve optimality, we need to fix Q to be odd power of 2, and we need to choose P to be a character of order 3. In this case, resulting line system LP will be biangular with following angles, and if we insert these parameters into relative bound, we will see that it achieves equality. If Q is even power of 2, then there are no characters P of order 3, and thus this construction is impossible. And for any odd power of 2, there are exactly 2 such characters P of order 3, which are complex conjugates of each other, and hence they produce the same representation of this special linear group and the same line system. And as I mentioned before, the first member in this infinite family is a system of 63 lines with angles of 0 and 1/2, which lie in semi-dimensional vector space and corresponds to the roots of the vertex E7. And it happens that this line system is small enough to be constructed with pen and paper by using the machinery which was introduced on a couple previous slides. In order to construct it efficiently, we first need to observe that non-zero elements of the field L can be identified with invertible 2x2 matrices with entries in the field Fq, and therefore we can think that multiplicative group of the field L is a subgroup of this general linear group for the two. As a special case, since elements of the unit circle have norm 1, they must be contained in corresponding special linear group. And in order to generate corresponding pi system of P, we need just a matrix TGP corresponding to an element which generates unit circle. And once we have this matrix, we can obtain R lines in this line system by raising this matrix to powers and picking column vectors from resulting matrices. And since matrix TGP generates cyclic group of order Q+1, there will be at most of exactly Q+1 different matrices which can be obtained in this way. Okay, and now we can start our construction. First, we identify field with 8 elements with this quotient thing, and we can choose a generator of the multiplicative group of the field with 8 elements to be this element. We can extend field with 8 elements by a root of following quadratic polynomial with where this S is same as here. We can use these formulas for absolute trace and relative traces and knobs of fields.
Miguel?
Huh?
This is your 5-minute warning.
Okay, thank you.
Yep.
Okay, these expressions we already have seen in the notation section, and this expression will be used instead of usual definition of the absolute trace, since it's much simpler. Okay, now following element generates unit circle, and its corresponding matrix form is following. So the corresponding matrix TGP must be of the following form according to the slide 11. And in order to compute entries, explicit entries of this matrix TGP, we first need to compute values of these two functions on the invertible elements of the field with 8 elements. Okay, and that's what we are going to do. Here are values of multiplicative character on the unit circle, and here are values of additive character of the field L on all circles of the field L. In order to compute the best values of the Bessel function, according to provided formula, we need to multiply a column corresponding to values of the multiplicative character with columns corresponding to values of additive character on the circles of the field L, and to compute sums. Okay, and this is done in this small table. On the unit circle, we have value 1/2, and this is computed by simply multiplying this element by this element and all the way down, and by computing the sum and by dividing by the q, which is 8 in this case, according to the formula of the Bessel function. And our other values are computed in a similar way. And similarly, we can compute also values of this function on all invertible elements of the multiplicative group of field with 8 elements. And by using these values, we can insert them into this formula to compute this matrix TGP explicitly, and it will be exactly this matrix. I omitted the character P from description of this matrix since it's hard to fit all matrices into the same slide. Okay, but now once we have computed matrix TGP, we just keep raising it to powers, and once we raise it to 9th power, we get identity matrix. So now our lines can be represented by columns of these 9 orthogonal matrices. And the resulting line system will be combination of standard bases and 8 mutually unbiased vacuum bases. Okay, and finally, once we are done with this example, I give a sketch of the proof of the optimality of line systems with corresponding to characters P of the third order. First, we note that angle set of such line system consists from 0, which comes from monomial matrices, as well from absolute values of the Bessel functions. So we need to prove that values of the Bessel functions are all contained in this set. We notice that multiplicative characters, that all multiplicative characters of the field L can be uniquely represented as products of 2 different multiplicative characters of the field L, which are constants circles R times C and lines T times F star respectively. And by the way, this rho doesn't is not related to the rho which describe a root of reducible polynomials. I just ran out of the good candidates for the names of multiplicative characters. Okay, so for all t in the unit circle, values of character p star on lines, like radial lines, are in one-to-one correspondence with values of some other multiplicative character of the unit circle. And okay. And now we can start. Instead of directly computing character sums of the Bessel functions, we investigate a lot simpler character sums, where instead of summing over unit circle, we sum over whole multiplicative group of the field L. And it's easy to notice that this character sum is a Gaussian sum for characters for following additive and multiplicative characters of field L. But on the other hand, if we first perform summation along the circles of the field L, we obtain values of the Bessel functions multiplied by values of this multiplicative character rho star. And this is essentially inverse Fourier transform of the Bessel function. So we have two alternative expressions for the same character sum. And we will concentrate into this case. Since this character sum is related to the field L, which in turn is extension of field FQ, we might hope that it's possible to express this Gaussian sum as a combination of Gaussian sums related to smaller field FQ. And it's indeed possible to do for all non-trivial characters rho star by using Hasse-Davenport product and lifting relations. And for character of degree 3, the result looks like this formula. For non-trivial character rho, value of the function f is a product of two following Gaussian sums which are related to field FQ instead of field L. This doesn't work for the trivial character, but instead we can compute this value explicitly. And it is cool. We might notice that we were only able to compute value of function f rho star up to sign. But if we imagine that we could always select sign to be a plus sign, it will be possible to write a following expression for the function f. Here we have replaced Gaussian sums by explicit expressions, and since values of Gaussian sums are -1 at trivial character. We need to correct that by introducing another term which corrects that the value of f at trivial character is exactly 2. Sign issue will not be addressed in this talk, and if you want, you can read the preprint. So once we obtain this expression for the function f, the rest is very simple. We perform following change of variables, and we rewrite the double sum in previous equation into this one. After that, we are able to integrate this term into this sum by simply removing star from the summation. And it's because by introducing constant to this function and performing Fourier transform of it, we essentially get a delta spike. So it's possible to do. But now we can compare expression for the function f, which is obtained here, with the expression for the same function, which we see here, and see that in first case we have it is inverse Fourier transform of the Bessel function, and in the second case it's the Fourier transform of the following function. So these two functions must be equal, and therefore Bessel function is same as this character sum. But it's well known that this character sum, that our evaluations of these character sums are always in this set. This is a result of Karlitz, and it is exactly which we wanted to prove. Okay, and thank you for listening.
All right. Thank you so much, Mikhail. I'm going to smash that reaction button. And I encourage you guys to do the same thing. And if there are any questions,